You got it? Yep. I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for the weekend just completed. Thank you that you spared us the rain, well, the flooding at least. Pray be with us today. Help us to glorify you, Lord, in what we do. I just pray that the students would be able to wrap up their homework before the break, and they have a good rest and time to connect back with their family or whatever it is that they want to do. Lord, in your name I pray. Amen. Okay, questions? Yes. 59. I did 59 last time. Oh, wait a minute, 58. I'm sorry, 59, not 58. Let's see here. Show that if f is differentiable at each point in the line segment PQ, and f of p is equal to f of q. So you got a line segment. Here's a point P. Here's a point Q. You've got a line segment PQ. Here's PQ. And we're also, what other data are we given? F of P is equal to F of Q. Then there exists a point R between P and Q for which the gradient of F at R is orthogonal to the PQ vector. We're given that F is differentiable at each point. Now, I suppose you could think of this as being a two-dimensional problem. You could think of it as being a three-dimensional problem. I think you could think of it as being an n-dimensional problem. So the most interesting way to interpret this problem is to say that f is a function from Rn to R. It's a real valued function, right? I think otherwise the question becomes harder to understand. So let us understand that that's the context. What do you guys want? Let's do R3. But I mean, I think the argument, we should be able to do it for Rn. So your f is a function from R3 to R. And you're supposed to show that there exists some point in between here, say R, such that the gradient of f at the point R is perpendicular to the PQ vector, right? Which you could write as what? That's Q minus P, right? So I don't know. How would you do it? Yeah.
Use the dot product.
With what and what? I mean, to show that this is orthogonal, yeah. But we would, yeah. I mean, we're trying to find the point R is the question, though. I mean, how do you provide the existence of such a point R? What is this? I mean, it's kind of sort of like the mean value theorem, right? Do you guys remember what the mean value theorem said from Calc 1? If you have a function, say from reals to the reals, and then if f is continuous on a, b, and if f is differentiable on the open set from a to b, then there exists c in the interval from a to b such that what? F prime of c is equal to f of b minus f of a over b minus a. So this was the so-called mean value theorem. For some reason, my mind jumps to this as I look at this problem. It's kind of sort of, I mean, it's we need some kind of existence theorem to get the point R, right? No. I don't think so. At least if it was that, then it's not stated in the problem. Well, I don't know. I mean, I suppose the thing I would be tempted to look at, since we've been talking about the chain rule, right? Why don't we, how can we make this a problem about calculus 1? How can we use existence theorems in calculus 1 on this problem? Like, we need to somehow convert this to a problem about a function of one variable. Any ideas? How do we gain information about a function of several variables? I mean, what we've done before in like partial derivative differentiation is we took the function and then we fed it a line in a particular direction, right? And then by differentiating the function composed of the line, that gave us the rate of change of the function along that direction. We called that a partial derivative or a directional derivative. I think we can use the same kind of idea here. What we should do is we should let g of t equal the function evaluated at a line which goes from p to q. And why don't we go back to like week 1? We learned to parameterize the line from p to q. How do we do it? Well, I'll say r of t. What was r of t was what? We used what? We did p plus t times q minus p, right? And that was for 0 less than or equal to t less than or equal to 1. You remember that? That gives me a line which goes from point P to point Q between time 0 and time 1. Yes, sir?
Where exactly is the line? What does R mean in terms of the function? Because I sort of see, it talks about P and Q being on a function somewhere.
We don't know what R is. That's the mystery.
It's just some random
The question is to show that there exists a point R at which the gradient is perpendicular to the
So is R on the function or not necessarily?
R has to be a point on the. I said R is a point on the line segment. So like R is an element of PQ. It's somewhere on that point. It's somewhere on that line segment. But that's pretty much all that I've said about it. You're not given R. You're trying to show that it exists. That's the problem. So you're trying to show that there exists this point R such that the gradient is perpendicular. The gradient evaluated at R is perpendicular to the PQ vector. I mean, on the face of it, it's a bizarre claim, right? I mean, I look at it and go, why on earth would that be true? I don't know, right? I mean, I could look at an example or something. That wouldn't be a proof, right? So I'm trying to use, I think maybe this. I'm not sure if this is the one to use or not, but this is an existence theorem that maybe I can use if I look at this the right way. So let g of t be f of the line segment from p to q, which would be p plus t times q minus p, right? Now, this g that we just made up, right? Because how many existence theorems do we know about functions of several variables and their gradient vectors? I haven't covered any for you in here, right? There are some in the textbook. In fact, there's a mean value theorem in the textbook, right? That I have not covered in lecture. Perhaps I should. Maybe tomorrow. But anyway, I haven't covered it yet. And I guess I haven't given you homework. Have I given you homework on it? I don't think so. Maybe some of the recommended homework. Perhaps we should work that tomorrow. All right, so getting back to here. Is this continuous? So think about AB being 0 to 1. It's continuous. Is it differentiable? Yeah, if I assume f is differentiable, then f composed with a line is certainly differentiable. And so I can apply the mean value theorem, right? And if I do that, what does that give me? G prime of c is equal to f, well, it's equal to what? G of 1 minus g of 0 over 1 minus 0. What would this be though?
C minus Q over what?
I think it would be f of what? F of q minus f of p, right? Divided by 1. And what's g prime of t equal to? Well, no, d dt of f of this function, right? So I got to do the chain rule. It's the gradient of f at the function dotted with the parameterization. So it's the gradient of f at r of t dot dr dt. But what is that actually here? Is what? It's fx at the point, right? Fx at r of t, fy at r of t, dotted with dr. What is dr dt here? Well, dr dt is the q minus p vector, right? If you calculate dr dt, p and q are constants, right? They're constant points. So you just differentiate the t. It leaves you with q minus p. So we have then, so therefore what do we have? We have f of, let me recollect our thoughts here, f of q minus f of p is equal to fx at r of t. Excuse me, I should be more clear here. At r of c, right? Why do I put a c there? So these two steps right here, I'm just calculating the derivative. Right? This, I'm using the mean value theorem. The mean value theorem says this, that there exists a c in the open interval from 0 to 1. I really shouldn't write any more. I will have solved the problem. Yes?
That's just the value of q minus p, right?
Yeah, I'm sorry. Let me make my parentheses be more curvy. There. So you tell me, what can you say about r of c? Where is r of c? If c is a parameter value between 0 and 1, what do you want to call r of c? What should you label it? Yes, it is the r we were looking for. And why does that show it's perpendicular? Like, what were we given I haven't used yet? We were given f of p is equal to f of q, right? So that makes the left-hand side be 0. So you got 0 is equal to gradient at r dot q minus p is, I'm sorry, I seem to have solved the problem. But you should write it in a way that is legible and your grandmother could understand. Sorry if your grandmother has passed. That dust is the worst. Anyway. So in short, you got to think about using the mean value theorem from Calculus 1 on the appropriate twist of the function. This is our go-to idea is to take the function and evaluate it at a line to gain insight about the function along a line. Yep.
Draw a two-dimensional example of a function with that line. I still don't get how that relates to the function itself.
Let's see here. So let's take f of xy equal to, I'll do something easy, x squared plus y squared. That's my favorite example. And let's look at this point and that point. Say 1, 1 and minus 1, minus 1. So I'm thinking of that as being the P, and this is the Q. So the level curves for this are obviously this, as we've talked about ad nauseum, right? Well, I'm not sick of it. I shouldn't say you're sick of it. So there's the level curves of F. And then, of course, you can see that f of p is equal to f of q, right? So there's my pq. F of p is equal to f of q, right? Which is what? Dose 2. And so the claim is that the gradient of f is somewhere between there, perpendicular to what? We're supposed to show what? That there's a point r somewhere on that line segment, that the gradient of r is what? See, have I satisfied the conditions? PQ. Huh. Oh. Oh, this is very frustrating, right? Because the gradient for f is like this, right? The gradient is like this. The gradient's like this. It's like this. Right? There's the gradient of f. That's what it looks like. Oh, no. Oh, no. How is this? How can this be? How have we proved something that's clearly not true for this example? Mean value theorem doesn't say it has to be happening at more than one point or lots of points. It just says that there exists one point. What is that one point? Yeah, the middle. The origin right there, that's where the gradient of f at 0, 0 is equal to 0, 0. So that's perpendicular to every stupid thing you can think of. So this is not the most exciting example, sorry, but it's an example.
Perpendicular to everything there is.
So I guess we need something more to make it fun, right? So if you have like this point and this point, right? And so this is one level curve of a function of two variables. This may be more instructive without the formula, right? So here's my line segment. And you can look at the gradients. Like so, like so, like so, like so, like so. As you can see, there has to be that point somewhere in there which is perpendicular to that line. So if you drew the right picture, you probably would convince yourself there's nothing to prove. It's obvious from my picture, right? If you believe in geometric proof. Some people do, some people don't. People who do are called geometers. Anyway. Ooh. Some sort of like amoeba with a spiky hair thing or something. I'll give it an eye. There we go. It's better.
It's a peanut monster.
It's a peanut monster. Other questions? Before I say more silly things. If you like that problem, you might be a math major. Yes.
Find the normal vector field for a
an, oh, sure. The normal vector field to a level function. That is not a bad question. So here's the example I should have showed you guys the first day we covered this. What's the one thing we know about the normal to before we talk about gradients? How about this? Ax plus by plus cz is equal to d, right? Well, look at that. That's a level function. You have f of x, y, z equals to some constant d. So this is a level surface. Of course, we should remember from like week 2 or week 1 even, I forget exactly, it's a plane. What's the normal? Yeah, this is a plane with normal ABC. So from the perspective of normal vector field, it's kind of an unnecessary concept for the plane because the normal is the same everywhere, right? So the vector field is constant. It's just always the application of the ABC vector. Now, how do we discover that? How do we rediscover that, rather, from the gradient? Well, it's simple. The gradient vector field is the normal to the level surface. See this? So we do partial xf, partial yf, partial zf, which works out to ABC again, right? Again, let me just write a sentence. This is the normal vector field. For f of x, y, z equal to constant. To give you a more exciting example, we could have something like f of x, y, z equal to xy minus z. So that's one of our standard examples from that we were hoping maybe I might have tested you on test 1. It's kind of nasty. What's the name of this thing if I set this equal to 0? You can also think of this as a graph. What is it? I think this is the hyperboloid, right? It's unpleasant. It increases in certain directions. It drops off in others as you think about the graph. It's got like a saddle shape, right? Anyway, so what's the gradient? What's the normal vector field to the surface? Well, calculate the gradient of f. So I got, y, x, minus 1. So the normal vector field at the point x, comma, y, comma, z to the surface is that, y, x, minus 1. So for example, if I focused on, I forget exactly what this thing looks like. I don't know. It's something like, so if I focused on that point, 0, 0, 0, which is on the surface, then the normal to that would be what? Right. So minus z hat, if you like. It has like a horizontal tangent plane there, but that's the only place, by the way. Everywhere else, the tangent plane is tilted on the hyperboloid, right? If I was to look at the tangent plane over here, it wouldn't be a horizontal tangent plane. It would have some kind of slope to it. Thinking of z equals to constant as being a horizontal plane in this discussion. What was the other way we found normal vector fields? If we are given a parameterization of the surface, we do what? We calculate the partial velocity and we cross them, right? That was the other way. Is there another question? Yes, sir. So what precisely about 57 would you like to know? I mean, where to get started with it? Sure. For problem 57, now that's an n-dimensional problem. So I'm going to show you n equals to 2. I'm going to show you how I would think about it in n equals to 2, but I want your solution to be in n variables, okay? But if you understand what I'm going to do for 2 dimensions, you can easily extrapolate to n. So you're supposed to do different things, like calculate the gradient of r, right? Among other things, what else was it? Gradient of r squared. What else? Gradient of 1 over r. Now here, r would actually be the square root of x squared plus y squared, right? Now, there's different ways you could attack this. You could just attack it just straightforward. What would the gradient of r be? Which would be what? Twos cancel. We got what, x over r. So you could write this 1 over r xy. I think in this problem I also encourage us to say that our vector is xy, right? So I can express this as the gradient of r is 1 over r vector. The calculation in n dimensions actually goes the same. You just keep going. Now, I think, that's not a wrong way to do it, but there's a lazier way to do it. Let me show you. So a lazier way to do it, I think maybe even a better way to do it, would be to look at it like this. This is r squared is equal to x squared plus y squared, right? So I'm going to use the method of differentials to simplify my life. R squared is equal to x squared plus y squared. So I can take the differential of both sides. And on the left-hand side, I get 2r dr. Oh, sorry, that was awful. 2x dx plus 2y dy. Divide by r, cancel the 2's. Dr is equal to x over r dx plus y over r dy. So therefore, the gradient of r is x over r, y over r. I never differentiated a square root there, right? Now, I was trying to get you guys to see this idea in a previous somewhat preachy homework problem I assigned you. Where was that? Or is this that one? No, this is not the one. Oh, never mind. I'm thinking of another calculus class I'm currently teaching. That's the trouble. All I teach is calculus. Sometimes it runs together. Now, your class does not usually run into my 126 class. Every once in a while, the 126 class runs into this one. And every once in a while, this one runs into the advanced calculus. This is one of those places. So, okay. So anyway, let me not get distracted. So then, how would you calculate? If you want to calculate the gradient of h, how to say this? So I don't know. How would you calculate the gradient of r squared? Would that work? How would that work? I do believe it works like this. That's 2r gradient of r. And more generally speaking, if we have the gradient of a function h of r, it will be h prime of r times the gradient of r. That's just the chain rule as it appears here. Sorry, of r. So, I mean, pretty much it's just a calculation, this problem. Yeah.
There's two different gradients of R that you solve for, so which one are you
I mean, I like the answer in terms of the R vector. I think that's the nicest answer. So I think this, I was just pointing out that it matches this one. I stopped short of going the one extra step, which is to say, oh, look at that. It's 1 over R times R, right? But they are the same answer. I mean, I think this is the best answer. Now, something you guys haven't asked me yet, but you should ask me at some point or another is, when is the total derivative and the partial derivative the same? When are they different? When is there an opportunity for being confused about which is which? I want to show you that. So suppose you have a function, which is a function of, say, t and g of t. Right? If you differentiated that with respect to time, what would you have? Chain rule says I have partial f, partial x, times dt dt, plus partial f, partial y times dg dt. Right? So nobody should be particularly confused by this. I mean, we can simplify this a little bit more. We have partial f, partial x, plus partial f, partial y dg dt. Okay, there it is. Where are these partial derivatives evaluated at, to be more pedantic? I mean, t comma g of t, right? I mean, that's the way the chain rule works. Outside function evaluated at inside. Right? I take the derivative of the outside function, but then it's evaluated at the inside function, right? And then multiplied by the inside derivative of the inside function. The wrinkle being we take linear combinations of the change in each direction. That's the chain rule for multivariate. Yes?
You mean to give dt of the, or partial f, partial x, dt, was that supposed to be partial
Yeah.
f, partial x?
Yeah.
Oh, I see.
So you're like, well, this isn't, I mean, maybe you shouldn't be confused. Let me say that. You shouldn't be confused by this. This is just the chain rule, right? Now here's a way to make it confusing. This could be rewritten as follows. df dx is equal to partial f, partial x, plus partial f, partial y, dy dt. Oh, dy dx, rather. Here I let t equal to x. So this expression I just wrote in green, it has overloaded the meaning of x as two different things. First, the parameter of a curve, right? A graph, really. Y is equal to f of x. Ooh, bad letter. Y is equal to g of x. And second, the variable, the first variable in the plane, the Cartesian coordinate x. But in this sense, partial f, partial x, and df dx can both be found in the same expression and yet be different. As you can see, they're not equal. So here's the careful meaning of what this is. Just let t equal x. There's another thing I'd like to talk to you guys about. I'm not sure I have enough time right now, though, so let me check for a second. When do we end? 4:05? Oh, 10 minutes. Good. So guys, when was it possible? When was it possible to solve f vector field equal to the gradient of f? So let's suppose f was pq, right? When is it possible to solve this as partial f partial x, partial f partial y? We've hit some homework problems on this, and I've started to discuss it in class, but we haven't. I'd like to get the ball rolling a little bit further on this discussion. When is it possible to find, if it's possible, if such little f exists, then the vector field f is called conservative. Really, this should be done with respect to some collection of points, some domain, as we'll learn. But what do you need? Well, remember, if these are nice, we have this condition, right? Partial squared f partial x partial y is equal to partial squared f partial y partial x, right? That's a necessary condition. The partial derivatives have to commute, right? So if both p and q are built from differentiating one single potential function f, the little f is called a potential function, right? What does that say about p and q? Partial x of q is equal to partial y of p. Now there's something, another way we could look at this. We could look at this in terms of a differential form. If we have omega is equal to p dx plus q dy, right? We said that was equal to df when same thing, right? That was the condition we needed for exactness, as we saw. Not having this condition made it impossible for us to find the level function. I might have called it, I forget, I might have called it big G in the lecture, I forget, but. Is there some kind of like sneaky way you could encode this idea using some other heuristic calculation? Well, there is. There's something called the exterior derivative. And so what's the exterior derivative? You've already seen the start of it. df is equal to partial f partial x dx plus partial f partial y dy. But the next level up is if I take the derivative of, say, omega, it's equal to dp wedge dx plus dq wedge dy. Now you could say, what are those wedges? Well, just think of them as being formal things I'm not going to really define for you, except to say that they keep track of a heuristic, all right? Like, just think of it as a placeholder for an idea at the moment. Anyway, if you'll set aside your questions about what in the world is wedges for just a second. We already know what dp is. dp is what? Partial p partial x, right? dx plus partial p partial y dy. So I take that wedge dx and then plus partial q partial x dx plus partial q partial y dy. So the critical thing about this new symbol I'm introducing, this wedge product, is it's kind of like it's like the cross product, but it's a little bit nice. I mean, it has distributive properties. It's actually also associative. But the one thing that makes it the wedge is that dx wedge dx is equal to 0, and dy wedge dy is equal to 0. on the flip side, dx wedge dy is equal to minus dy wedge dx. So it's a lot like the cross product, all right? It's a lot like the cross product. And so with that rule, and if you can, distribute, what does this give you? Like you get dx wedge dx when you distribute. So that term's 0. So I get, basically, I'll drop the terms which are 0. I get partial p partial y dy wedge dx plus partial q partial x dx wedge dy. So what is this? Well, partial q partial x minus partial p partial y dx wedge dy. So you see, the condition that omega be exact, it turns out to imply that this exterior derivative, this d omega, has to be what? What's that condition become here? These cancel, right? This is 0 if omega is exact. So if the exterior derivative of omega is 0, then we say that omega is said to be closed. It's a closed differential form. So exact always implies closed. The reason I'm telling you this is there's something kind of fantastic that happens if you were to look at a vector field PQR, right? And if you were asked the question, is it equal to the gradient of some function of 3 variables? Do you know what you can do? One of the necessary conditions, you can look at PDX plus QDY plus RDZ, and you can take the total differential of that. I mean, you can take the exterior derivative of that. And when you do that, this equals to 0 gives the 3 necessary conditions, 3 needed conditions between P, Q, and R in order that you can find a potential whose gradient gives you back the vector field of 3 variables. So this, in a very natural way, this calculation I just showed you generalizes to show you what's analogous to this condition in higher dimensions. In 2 dimensions, we just need this one condition. But if there's more components to your vector field, you need more intertwining conditions in order to make sure that this partial derivatives commuting match up. If you have 3 variables, you have more partial derivatives to match up. You got x with x with y, you got x with z, and you got y with z. Those are the 3 conditions, those 3 partial derivatives commuting. That's all wrapped up into saying that the total derivative, the exterior derivative of that thing is 0. Anyway, I'll tell you what, if we have time tomorrow, I'll show you if you're interested. If you're not, I'll let you go on your break. So, is there a question?
Is there any way we can extend the test next week to Thursday?
Well, if I extend the test to Thursday, then that would mean I'm covering new material at the start of next week. So it's not wise. I mean, it's not ideal. I think the test is as stated. But by then it should be by now you're already bored with chain rules, right? You're like, another chain rule. I know these already, right? No? No? It's a chain rule. It's harmless. You can calculate partial derivatives, yes. This test is not so bad. It's certainly not as bad as the first test. There's not so much geometry in this one, right? No? I'm sorry, I think I need a stronger reason than birthday to move the test. No offense, but that wasn't the reason.